Okay, so in the last video we ended up talking about the mechanism of both the SN2 and the SN1 substitution. All right, and what makes the SN1 different is that it initially proceeds by the step where a group leaves, and that creates this carbocation, and the nucleophile then will attack the electrophile. All right. And the thing about this is that since it's flat, you could either get attack from the left side or the right side. All right, and depending on which side the attack occurs from, you're going to get two different processes. All right, so the reason we have evidence for this mechanism is that if you change the amounts of things, or remember in this reaction we have both the alkyl halide, all right, and we also have your nucleophile. All right, and what was found is that the overall reaction only depended on the amounts of the halogenoalkane, all right, or the alkyl halide. All right, and that's because this right here is the slow step in the mechanism. All right, so that's when they say that this is an SN1 reaction, the one comes from the fact that there's only one chemical in the rate equation. All right, so if you're to come up with a mechanism, this step right here is the slow step, this step right here is the fast step, and so this is the only thing, this species would be the only thing that shows up in the rate equation. All right, so what are some things that affect whether or not an SN1 reaction or an SN2 reaction occur? All right, first is going to be the effect of the solvent. All right, SN1 reactions are helped out whenever you use a polar protic solvent like either water or ethanol. All right, so what makes something a protic solvent means that essentially it's got an OH or an NH bond. All right, and the hydrogen, remember a lot of times hydrogens that can be pulled away are referred to as protons, so that's why that is considered a protic solvent. All right, it's another way of saying this is that if you're a strong enough base, it's a material that you could pull a proton from. All right, so the reason that these help out with SN1 is that the SN1 reaction requires this carbocation intermediate. All right, so if this thing is going to survive in a solution, it needs to be stabilized somehow. All right, and solvents like water and ethanol can help out by donating their electron pairs temporarily to that carbocation. All right, and that helps this thing stick around for long enough for a nucleophile to come in and do the second part of the reaction. All right. By comparison, SN2 reactions are aided by polar aprotic solvent. All right, aprotic means non-protic. All right, it's something that's not got the ability to give an H plus to something else. All right, so some examples of those would be things like diethyl ether, which is commonly referred to as just plain old ether. If you wanted to use the IUPAC name, it would be ethoxyethane. But another very common aprotic polar solvent is dimethyl sulfoxide. All right, so and this right here is the structure for dimethyl sulfoxide. It's commonly referred to as DMSO. Why is this helped by these solvents? Well, the SN2 reaction requires to get them to work, you need to have a stronger nucleophile than you do for the SN1. All right, and if you did that, the polar protic solvents would interact with that solvent. All right. So the thing about these two solvents right here is that they're polar enough to solubilize the nucleophile, but they're not. But they won't react with it, and so it's a nice compromise. All right. I would say that DMSO is probably by far the most common solvent used for this. It's used much more common than ethoxyethane, or sorry, ether. So some other things that are going to affect this reaction is going to be the nature of the nucleophile. All right. In general, anions tend to be better nucleophile than the corresponding neutral molecule. All right. So just as an example of that, we're going to consider water right here. All right. The lone pairs on the water aren't that nucleophilic. All right. And that's because the oxygen is relatively electrophilic. It likes to pull electrons towards it, and that prevents these electrons from being that successful as nucleophiles. All right. But if you're able to deprotonate this, to abstract an H+, all right, so let's take this H+ away, and remember, if you took the H+ away, and again, that would require a base to pull that away, these electron pairs go onto the oxygen. That gives it a third electron pair. All right. By comparison to water's oxygen, the hydroxide oxygen is way richer in electrons. All right. So this is so electron rich that it increases the nucleophilicity of these electron pairs. All right. The same thing could be said of an alkoxide as compared to an alcohol. All right. So again, if this electron pair right here forms a bond to an H+, this would essentially be an alcohol. All right. So alcohols aren't that nucleophilic, but if you use a really strong base and you pluck that H+ away to make this this alkoxide, this is going to be much more nucleophilic. All right. So one other thing that's going to commonly act as a nucleophile are going to be amines. All right. And so there are three. I've actually shown 4 different varieties of amines. All right. So at the top, this would be a tertiary amine. All right, meaning you've got 3 carbons directly attached to the nitrogen. This would be a secondary amine, which means you've only got 2 carbons attached. This is a primary amine, and this one right here, well, remember there's only one of this. That's just going to be ammonia right there. All right. So since the nitrogen is less electronegative than oxygen, amines are more nucleophilic than alcohols. All right. In general, they will act as nucleophiles even if you don't make the anion. All right, so like you don't need to remove one of these hydrogens for this nitrogen to act as a nucleophile. All right, so what about your electrophile? All right, in a lot of these reactions here, we had some type of alkyl halide. All right, and this could be bromine, it could be chlorine, or it can be iodine. All right, so which is the most effective type if you want it to act as an electrophile? Well, iodides tend to be the best electrophiles. Right? They're the fastest reacting of all of these, and the reason for that is that the bond, the carbon-iodine bond, is relatively weak. All right. So remember, in order for this reaction to occur, this bond right here has to get broken. All right. And so it's much the iodine is this bond is much easier to break for a carbon-iodine bond than it is for these right here. All right. Last factor that we want to mention is primary versus tertiary versus secondary carbocations. All right. So remember in the SN1 reaction, first the bromine leaves, and that creates this tertiary carbocation. All right. So if this right here, if this group right here were to be a hydrogen, that would be a secondary carbocation. All right. If this and this were to be hydrogens, that would be a primary carbocation because it would only have one carbon directly attached to it. All right. So in general, whenever you can make a tertiary carbocation, that's going to favor the SN1 reaction. All right. If this right here is a hydrogen, you would get either SN1 or SN2. All right, so when you get essentially where you've got 2 carbons directly attached, either mechanism can go. But if these were both, if both of these right here were to be hydrogens, or if all 3 of these right here were to be hydrogens, that would definitely favor the SN2 mechanism. All right, and the reason for that is if let's say, for example, this and this, instead of being methyl groups, were hydrogens, well, in order for the SN1 reaction to occur, that would involve creating a primary carbocation, and those aren't stable. All right, so they wouldn't exist, so we couldn't have that mechanism. All right, but notice that with the SN2 reaction, go back to that up here, notice that you never end up forming that carbocation intermediate. All right, so for that reason, this reaction can happen just as well with those kind of electrophiles. All right, so that's it for the introduction to electrophiles and nucleophiles. We will talk about some other organic reactions in the next video.